In 1973, Stephen Salter started looking for ways of generating electricity from ocean waves. He put various floats and flaps into a wave tank and made them work against a dynamometer, the two metal arms swinging up and down above the water. These experiments gave Steve the insights to develop a new asymmetric shape, which he called the duck. He found that it could absorb more than 80% of the power in the wave. Although others, including Edison, had looked at wave power, the publication of Steve's work in the journal Nature sparked off new activity around the world. As the British government started to fund the work of the new wave energy group, we built new test rigs and began detailed analysis of the duck. We also started to design full-scale seagoing systems. Ducks would be strung along a floating, segmented tubular spine, loosely moored several kilometres offshore. The interaction of wave energy devices and large ocean waves was so complex that few insights came to us from mathematical analysis. To optimize the many design variables, we had to do more realistic tank tests. Fortunately, with the duck, we could do this at very small scales by developing a new generation of wave makers, instruments, and rigs. In our narrow tank, the ultimate realism was now provided by the surging, heaving rig. Our single duck could pitch, heave, and surge, as if it was attached to a floating spine. The mechanical linkages of the rig decoupled the complex motions of the duck into a surge-only and a heave-only axis. The forces and motions were sensed by strain gauges and velocity sensors, and the models reacted against forces provided by amplifier-driven electric motors, as well as against actual masses and springs. On the other side of the rig, we can see the model being driven in calm water by the brushless, permanent magnet motor of the surge axis. The heart of the narrow tank was a bench covered with analog electronic circuits for measuring and controlling experiments. Glenn Keller built this one to simulate the gyroscope-based power takeoff system that we were then designing for the full-scale ducks. At that time, in the late 70s, it looked like the power system would need to be in a completely sealed container. The gyroscopes provided a way of doing this, and also gave us the stimulus to start developing a new generation of high-pressure oil hydraulic machines. Potentially, the gyroscopes gave us some useful energy storage, but later on, new materials enabled us to get rid of them. Two heaving float wave gauges in front of the model, and one behind, let us account for the lost energy that was reflected or that escaped downwave of the duck. We were obsessed with finding ways to increase the power conversion efficiency in long waves. Then our full-scale ducks would be smaller and the electricity as cheap as possible. This was our best beach, a wedge filled with expanded metal, a design that we went on to use in the wide tank. The efficiency meter shows that we were getting over 80% of the energy out of these fairly short waves. Long waves were harder but more valuable. If we made surge movements stiff, we only got 35% of the energy. However, we found that by making the axis movement more compliant and encouraging the model to move more, we could capture much more energy. This was a very important discovery, that the joints between spine sections would have to be active. In our narrow tank work, we learned a great deal about such strategies, ways of recovering more energy from the concrete and steel of a full-scale wave energy system. The final stage of realism possible in the narrow tank was to work with a mixed sea, something more like the randomness and variation of the ocean. By arranging the phasing or synchronization of different wavelengths, we were for the first time able to simulate ocean storms and to plan for duck survival in extreme waves. We had already built the wide tank to give us a facility for testing a fully realistic duck strain. We now needed nearly 100 models, each with an internal dynamometer and active spine joint. David Jeffrey developed the onboard electronic control loops and a time division multiplex system for connecting them to the remote command computer, which would give us real-time variation of the model characteristics from a control bench. We went into mass production and roped in school leavers, computer programmers and students to help us. Making so many parts work together and underwater was a real challenge. The model was now, outwardly at least, similar in most respects to the proposed full-scale system, and we had the same range of control that we'd enjoyed in the narrow tank experiments. We could vary the damping, like changing gear on a car, and also by feeding back other control terms, we could use the same dynamometer to change the apparent stiffness or inertia. To operate a wave power plant efficiently and give the best return on capital, the system needs a kind of intelligence so that it's able to tune into the currently prevailing wave spectrum and directionality. The spine joints were also active. Inside you can see one of the motors and drive belts. These allowed us to make the spine flex in a controlled way to give us more energy, particularly in long waves, and to limit the spine bending moments in big waves. We could also simulate the stiffness of full-scale spines that were made out of different materials such as concrete or steel. As well as its own electronics, each spine unit also housed the power amplifier for its duct. A DC motor with shaft-mounted gearbox drove a triangular torque plate through a maximum of plus and minus 4 degrees. A pair of toothed Kevlar reinforced belts coupled the torque plate to the motor. Spine units were arranged such that alternate joints were active in heave and surge. The key to control of the spine joint was to know the force or torque at each joint. We measured this with a full bridge arrangement of 4 strain gauges. Glenn Keller studied the problem of interfacing the complete wide tank duct and spine model to the various control computers. His system would have capacity for more than 1,000 channels of two-way analog and digital signals. Chris Retzler preparing the spine model. You can see a continuous line of electronics boards along the support structure above the model. We called this swimming. Spine joint motors were being exercised in still water, and we used it to check out the system before a test. By this time, in the early 80s, government policies discouraged further work on wave energy, but we were able to continue studying the spine. Much of this work has paid off in the recent development of Richard Yem's Palamas, a new generation of wave power device. In this test, an angled regular wave is being driven along the spine by the wave makers off to the right. It's hard to see individual joints bending because the angles are so small. It's easier to see the whole spine bend when we see it being hit by an extreme wave. Our tests told us about the likely behaviour of wave energy systems in powerful seas like those off the Scottish west coast. Each of these test seas represents a measured South US sea state with a unique mix of wind sea, swell and old wind sea. Over the years we'd gathered the basic knowledge for the engineering of full-scale duct strings that would be energy efficient and seaworthy. A decade or so later, our colleague David Pizer produced a powerful new tool, a computer-based modelling methodology that would allow us to rapidly explore alternative control strategies. The original funding for early British wave energy devices emphasised schemes comparable in output with coal or nuclear power stations. Because of our uncompromising attitude to high power capture and to survival in extreme seas, the duck is often referred to as a third-generation device. It has depended on new technologies such as digital hydraulics and of materials that are particularly tolerant of the marine environment. The projected cost of a unit of duck electricity has gone up and down over the years, but now we maintain close links with the economic model maintained by Tom Thorpe, the British Authority on Wave Energy Costs, and we predict ultimate costs equivalent to less than 3 pence per unit.